Yeah, if we look for accuracy, then we see that the P controller accuracy is poor, because this controller gain could not be larger than, let's say, 4 or 5, otherwise we get bad damping. This is given from process, cannot be changed. So what we can do is, can we look for another type where this is larger, maybe then with more stability, more better damping. And we find a solution. If you look into the workbook, page 16, what I have mentioned is, for example, here with my I block, if I use a pure integrator as a controller, then I have the advantage that if P is 0 in the denominator, we have a 0, then the gain goes to infinity. So with an integrator, and I have told you in another video, each block type with an I in the name has exactly this property. If there is a P in the denominator, a pure P, we set P to 0, we get infinity large DC gain. This should be checked. Yeah. So the next trial of controller type is a pure integrator. That is chapter 5.2.4, I controller. And what I've mentioned, I want to have now all the other new controllers with the same value of damping indicator phase margin is 60 degree. Okay, Nyquist is the base, and we go to the open loop phase equation at omega d is minus 180 plus 60. So we have now the situation that the open loop phase at omega d is minus 120, unchanged, same as 5.2.1 P controller. But what is new is the open loop phase now at omega d is controller phase plus process actuator sensor phase. And now you see what happens. The I controller has a phase. How large is the phase of the I controller? Here you see it. An integrator has a constant phase value of minus 90. Consequence is, this is minus 90 degree. That this is minus 120. The controller brings a large negative part. So for the process, there is only now a small range possible. We can solve this for the process phase, PAS, which is then negative 120 plus 90. Negative 120 plus 90 is negative 30. And at omega d, yeah, at andersrum, at omega d. That finally gives the new solution. I go back to workbook, page 38, and in this page we go into my process Bode plot. I shift this a little bit larger. Now we have to look not at minus 120 but minus 30. That is this point between the second and third line, and you see here between second and third line, between this value and that value, this value crosses exactly the minus 30 degree line. So we are now at this point at minus 30 degree, or in other words, here we go with our omega d value to 0.1, 2, 3, 4, 4. That is the value. Cross point is at 0.4. The result is omega d now is 0.4 per second. Now compare with same phase margin with P. Omega dP was 2.6 per second. This is a factor 6.5. Slower. Yeah, now we see omega d is a speed indicator. That was a P controller speed. And here the price I have to pay for this high accuracy of the eye controller, the price is a very big speed decrease. We are very, very slow. 6.5 times slower than a P controller. But we have exact accuracy. Yeah? Very slow, but exact. That's the result of my eye controller. In my paper, in my workbook, there is a new diagram. What I have done here is very simple. I have added to my process phase, the red curve, I have added now the controller phase and get the green curve. That is the open loop phase, the green curve. So the distance between red and green is at any frequency 90 degree negative. Yeah? So I shift the red curve with 90 degrees down and get then the green curve. And then the open loop phase, green curve cross point at minus 120 gives our 4. And here you see our magnitude value, of course, is then we have not discussed magnitude values. The cross point is at the same radian frequency here in exact values with numeric support. I get a little bit smaller value, and the process magnitude, if I now look at 0.38 for the process magnitude, this is a little bit smaller than 6 dB. So 5.5 dB maybe we can read. So finally I can note to calculate Ki value, take the open loop at omega d equation is 1, the second Nyquist equation. And the second Nyquist equation delivers, so I think we have to add the controller transfer function, which is a Ki value unknown to be designed, divided by P. That is the transfer function of my controller, and I call this controller gain now Ki, which is not a DC gain, that is just the crossover frequency of my integrator. Yeah? The magnitude of the controller, is very simple. P replaced with j omega, and the magnitude of this is just Ki divided by omega. So that if I go into this expression, I calculate the following final result: the magnitude of the controller times the magnitude of my process actuator sensor at omega d should be 1. Yeah, what do we have? We have this from curve, positive 5.5 dB, and this is Ki and the unknown Ki divided by omega d. So we can solve this to Ki, which then is, so the equivalent of 5.5 dB we can find in my paper is 8.88. Yeah, 1.88. 1.88. 1.88. So the equation, the solution of this equation is Ki is equal 1 times omega d divided by this. So omega d divided by the process gain at omega d 1.88. This gives 0.4 per second divided by 1.88. So Kc is finally what I have calculated in this. Kc is 0.207. 0.207. Okay. Per second. Note this is the Ki value, that's the frequency, radian frequency. At this radian frequency, the gain of my integrator for a sinusoidal signal is exactly 1. But now we can test, we can simulate this. Simulation. See simulation. So I now go to my calculation here. I delete this curve because I want to show you now all responses with 60-degree phase margin. I close this window and go to the signal block diagram. I replace the P block. So I mark this, click on the delete button, and I add my integrator. And the Ki here is exactly this value, 0.207, calculated by my calculation just before. And now look what happens if I calculate the response. Yeah, clear. What happens is the following. Schnell weg. I was not careful. If I delete this block, this was block number 1, of course, then these blocks are renumbered. And the new block then gets the new number 5. So I want to have now the output block number 4. Okay. So I have to recalculate here this number and decrease to 4. And you see now what happens. This is unchanged. This is just block 5 output. But now you see here the block 4 output, and if I go to 20-second, you see what happens. There is a nice settling to the exact final value 1. So accuracy very high, but speed very low. We have a very slow system. The peak value here is at 7 seconds. We just check if we can calculate this with our estimator. And the overshoot is a little bit smaller than this. This is nearly 20%. Then this is, I think, 8%. That's rather okay for a 60-degree phase margin design. Yeah. So we can say with a pure integrator controller, gain is very good. The accuracy very good, but the speed is very, very poor. Simulation. Our Tmax is 4 divided by omega d. Very easy, we can check this. 0.4, that is 10 seconds. In simulation we get the calculated Tmax value, which is 7 seconds. Yeah? 7 seconds. So this is the inaccuracy of my speed of my reference step response Tmax value. Yeah? So that's very plus to minus 30% is not a real, we cannot get more accuracy than 30, 40, 50%. Yeah, but just an indicator, just an indicator. Okay, so we can say if we find a better one than this, we should do this, and we will do this in the next step. Okay, that is the next number, 5.2.5. The PI controller. What is already used in the both first projects? Let's look into this change of the controller type. First, a quick view into my page 16. Here you can see, okay, that a P controller has a naked P in the denominator. That means that at P0 DC case, again, this transfer function, so the gain of my controller, is infinitely large. So we can say the control error of the PI controller is as small as the pure I controller. Why could the PI be better? That I think could best explained at the phase curve of my I controller. Why is the I controller slow? Note that the cross point of the P controller with the red curve is here with a high omega d value. Then the negative phase shifts the curve down. That means at the same phase value, the omega d value is decreased, goes down. So negative phase means the speed goes down. So, so we can say in general, design rule is avoid negative phase, because same phase margin at negative phase, speed goes down. That is a fundamental relation, and that should be noted. So if you have the decision between two sensors, one sensor is a little bit has more negative phase as the other, take that with less negative phase, because negative phase makes loops slow. So if we can find a type of a controller which has the same DC gain, infinity, and less negative phase, then we have the same advantage than I, but we are faster. And that is exactly true with my PI. Let's have a quick look into the phase of the PI. Look on page 16. Go to the PI row, and finally to the, let's here this row 9. So, row 9. Look here, the phase curve starts with negative 90, but here you see that the phase curve goes up to 0. That means DC gain is infinity, makes control error 0, but the negative phase is not so negative compared with the integrator who has a constant minus 90 degree phase. So the PI is as good as I, but faster. And that is the reason why you have never seen a pure I controller. That was an intermediate step. This shows the PI controller is much better than an I. The design of an I comes now on the next point in detail. So let's make some notes. DC gain is infinity. Consequence, control error. Final value of the control error is 0. Same accuracy, but phase is more positive, you can say. More positive than I. Note I is constant minus 90. PI is minus 90 plus arc tangent omega Tn. So there is a positive term which is added to this minus 90 degree value, and this makes our PI controller faster. Okay, steps to design is we in this chapter 5.2.5 want to show the PI controller with pole compensation. Pole compensation means we have a 0 in the controller fc of p is, I just copy the transfer function, has a 0 in the numerator and 1 plus pt term in the numerator, and with this we can compensate a pole of the process. Pole compensation means Tn then is set to 1 of the time constant of the process. Note we have now the decision of 4 time constants. Which time constant should we compensate? That is the question. No? 10 millisecond, 1 second, 50 millisecond, or 330 millisecond. In all 4 cases we can call this pole compensation, but what is the best choice? I tell you what the best choice is. If we can remove the time constant which makes the worst effect, then we do the best. And what is the worst effect? It's the largest time constant, because the largest PT is the PT1 with the largest time constant makes the system slow with dominant effect. If we have smaller time constants, the effect to reduce speed in a PT1 system is smaller. So we have the best result if we compensate the largest process time constant. This is 1 second. So 1 second in parentheses largest process time constant. Because then we have the best effect. Then this deletes that 1 plus pt term which has a dominant speed decrease. Okay, so the pole compensation defines the choice of Tn, and now we can do the next step. Now add to the phase from the process and the actuator and sensor, add to the process phase of omega the controller phase of omega. Point by point we have to draw a new curve. Controller phase, which is written here, is minus 90 plus arc tangent omega Tn. Tn is selected to 1 second, so we can point by point now calculate the controller phase and add point for point to the given process phase curve. And this sum is then the open loop phase curve. Is process phase plus controller phase. This gives a new phase curve. We need this new phase curve because the cross point for my given phase margin, it has to be searched with the new phase curve. In my paper, we have now to look for this resulting phase curve. Here you see PI controller process for PT1 with pole compensation. Here you can see 3 curves. Unchanged magnitude of the process. The red is the process phase curve we have worked on, and the green curve now is the new added open loop phase. You see for low frequencies the phase shift is near to minus 90. The phase, the negative phase, becomes smaller and smaller if the frequency goes up. And you see here for frequencies in this region, the negative phase shift is much smaller than in the case of the eye controller, because the eye controller has for all points negative 90. That means the cross point at minus 120 with the new green open loop phase curve has now a crossover frequency which is in the near of 1.4. Here you see that is a result. Omega d is 1.4 per second. That means we have now a new result. We have to write down on page, what is it for a page number? The page number is 39. On page 39 in the workbook. Bottom part. Bottom curve. Green phase curve. Cross point at minus 120. We want to have the same phase margin, 60 degree, ends up in an omega d, which is 1.4 per second. If we compare this value with the eye controller, where is the value? The eye controller omega d value is 0.4. Yeah, the P controller 2.6, I 0.4, now PI 1.4. This is factor 3.5 faster than I block with the same accuracy. That means, yeah, my PI is just better. There is no disadvantage. The only thing is, in our operation amplifier circuit, we need now one resistor more. One resistor costs 1 cent. Yeah, so I think the price is the same. In digital controllers, we have some multiplications more, so we need more calculation time, but this is mostly neglectable. So many applications run with PI controller, because the PI controller has zero control error caused by the integrator and is acceptable fast, but note that this PI controller cannot reach the speed of a P controller. P controller is faster, has control error, but is faster. Let's finalize this design with the calculation of K and then the simulation of the PI controller. I think this should be done in the next video. This becomes video 52.